Today we're going to look at Fleming's left-hand motor rule. We've already established that a current-carrying wire creates a magnetic field. So if the conventional current is going that way, then we get circles around the wire. They get further apart as you go out, and in this case the fingers wrap and they tell us that that's the direction of the magnetic field. But the only rule we've got for predicting the force between magnets is that like poles repel. And in this particular picture, we have to say to ourselves, where's the pole? No sign of any pole that I can see. We've just got circles around the current. So Fleming has studied this, and he found that the three elements that we've got, the magnetic field, the electric current, and the force, are mutually perpendicular. And he cunningly spotted that a left hand showed exactly those characteristics if we hold it in the right way. So here's my left hand. Terrible picture, but never mind, it'll have to do. And make sure you remember it's the left hand. The left hand motor rule. And so I want you to get your left hand out and arrange these so that this is a right angle and this is a right angle and the other one's a right angle. So these three digits, the thumb, the first finger, and the second finger, are mutually perpendicular. Because that's what we find, is that if the first finger is the magnetic field and the second finger is the current, then the thumb is the direction of the force. So that's how we work it out. They are mutually perpendicular. Each one is perpendicular to the other. So I've highlighted that with some cunning color coordination for first finger field. First finger field. So we remember it by using a bit of alliteration, first finger field. And then second finger is conventional current. And then you've got a choice for the third one, but the thumb is either, some people say thumb thrust, other people say thumb force, and even there's some who say thumb motion. But ultimately, this is just an aid to memoir. Everybody uses it. Don't be ashamed, a bit like the right-hand grip rule. Get your left hand out, and let's hope it's better looking than my picture. And that will tell you the direction of the force. Okay, well now, if we go back to thinking how can we make something useful like an electric motor, then if I draw a picture of two pole pieces, north and south, and remind ourselves that the magnetic field goes from north to south, and this is a fairly uniform field. We can tell that because the field lines are roughly evenly spaced, and they're going from north to south. And then in the middle of this, I'm going to put a wire mutually perpendicular to the field. So this wire is like this, and I'm going to show it with the dot, and you will remember that a dot means that the current is coming towards us. So get your left hand out, and your first finger is going from north to south. The current is coming out of the page, so the force, as indicated by the thumb, will be upwards. So this is the way it works with electric currents. Now another way you can look on it, if you like this, is that we can start with our magnetic field created by these two poles, and we can introduce our current carrying wire first. And you will remember that the right-hand grip rule tells us that this will create a magnetic field going round anti-clockwise. So this interacts or adds to the other magnetic field. So what we find is that these magnetic field lines, this one here might still go across like that, but it's going in the opposite direction to the magnetic field, whereas this one will come like that, and like that, and like that. And you can tell me where you think the strongest region of magnetic field is and where the weakest region is. And people say, well, the field lines act a bit like an elastic band, and we can see that they're tighter round the bottom, and so that suggests the same thing, a force going up like this. Now in our next video we'll have a look and see how we can make this effect into a motor, but I've got a couple more things that I want to show you before we finish. You don't actually need the permanent magnets. What about if we've just got two current carrying wires? Okay, two current carrying wires. One like this, and one with the current going in the same direction. Okay, well what I'm going to do, I'm going to call these, what shall I call them, X and Y, so we can be clear which one I'm talking about. And I like to use green for magnetic field. So we use our right hand grip rule and we show the magnetic field going like that, and like this, and so on. And what I'm going to do is I'm going to draw this magnetic field out until we get to Y. So this is the magnetic field due to X that is experienced by Y. Okay, so Y is in the magnetic field, and the magnetic field is upwards. So with the assistance of our left-hand motor rule, we can show our first finger field pointing upwards on the page. Our second finger is the current. So the current is coming out of the page towards us. So our second finger is upwards. So we can see that this is going to produce a force towards the other wire. So perhaps surprisingly, these wires with currents going in the same direction do not repel. They attract each other. So we might say to ourselves, well, hang on a minute, what about the other one? Well, what I mean is, suppose we can look to the same situation here, but in this case, we're going to say, what's the magnetic field due to Y over at X? So here we go. We've again got the first finger field. So these going round like this, and the field's pretty strong close by, and it's going. I've just used my right hand grip rule to check that it's going in that direction, and it gets weaker as it goes out. But over here at X, we find that the magnetic field is going downwards in the picture, from the top of the page to the bottom of the page. Out with the left-hand motor rule, first finger field, it's downwards. Second finger current is coming out of the page, so it's quite tricky to actually twist your wrist round, but you can turn the computer or the page round instead, and we find that the force is going this way. Now that's just as well, because Newton's third law predicts that if the force of X on Y is a force of attraction, F, then the force of Y on X is a force of attraction. So this confirms Newton's third law. But what about the elastic band idea? Well, let's switch over here now to consider actually the currents going the other way. These two currents now, they're two long straight wires side by side, and now one of them's got current going one way, and one of them's got the current going the other way. Well, I've chosen this one because I know the magnetic field pattern for this is the same as the magnetic field pattern of a coil. Really close to the wire, it's pretty much a circle. As you go further away from the wire, then you get this sort of effect. Okay, and then finally we need to use our right-hand grip rule to decide which way these lines are going, and they're going this way. Okay, well, if these are elastic bands, then you could say to yourself, if these are elastic bands, they would be pushing these two wires apart. So that's in line with predictions, because having reversed the current in Y, then the force on Y is going to be reversed. Having reversed the current in Y, the magnetic field at X is going to be reversed. So both our pictures here that we started off with, what shall I do? Say number 1 and number 2 and number 3. Okay, so that's all I've got time for today. That introduced us to Fleming's left-hand motor rule with a wonderful picture of a hand. And so on our next video, we'll have a look and see how we can use this to make a DC motor that actually spins.